Hello everyone, and welcome to this additional multiple regression practice activity. So you have an additional practice activity worksheet on Blackboard, and it's designed to be structured in a similar kind of way to your assessment question. So what we're going to look at is how might you go about analysing regression data and kind of interpreting it in relation to these sorts of questions. Okay. So we have a question about what's the point of doing the multiple linear regression, what are we aiming to achieve, exploring the data suitability, so does our data meet all the assumptions for running a multiple linear regression, how effective is the regression model at actually predicting our outcome variable, and what kind of information we can use to help decide that. And then looking at the relationships, if there are any, between predictors and outcome variables, and kind of looking at whether our findings support the hypotheses or not. And then we'll be looking at, in combination, looking at how this information can be used for a future research project, so kind of future directions, or how it could have a practical application. So we'll touch on those. Really, I'm going to focus on performing the multiple linear regression and then interpreting it. So the data we have for the practice multiple linear regression is this one. So what we have an ID number. So what we can tell here, this is actually an ID in the order in which people participated in the research. We have a column about gender. So we've got gender and everyone identified as either male or female in this. We have an age in years, so age at last birthday. So this is measured as a ratio level variable. Then we have a measure of extrinsic career success and a measure of satisfaction with life. Now, if this was your research project, you'd probably want to be knowing, well, what on earth do these two things mean? So in this example, extrinsic career success means the higher the score, the more extrinsic career success that individual self-reports, and the higher the score on satisfaction with life, the greater their satisfaction with life. And we can see that scores range from 30 to 130 on the measure of extrinsic career success, and scores on life satisfaction range from 60 to 300. Now, you would want a lot more information here about those measures, how they worked, what how they've been validated, what their reliability is, and so on. But at the moment, this is all the information we have. So what we want to do, what the aim of this is to explore whether gender, age, and extrinsic career success, as self-reported, can help predict satisfaction with life. Okay. So what we might be anticipating is that there'll be a positive relationship between extrinsic career success and a positive relationship between with that and satisfaction with life. Okay. So what we're going to do, we're not sure in how gender and age will play into this, so it's fairly exploratory in nature. So we're going to do a standard multiple linear regression using this data. So the first thing we want to know is to get a sense of what's going on. So we would look at, say, the descriptive statistics for our data. So we can, one quick way of doing that is to actually right-click on the variable, and we can ask it to produce descriptive statistics. And here we have the frequency for males and females. So we can see there's no missing data. Everyone either identified as male or female. So that's useful. There is obviously the long-winded way of doing that as well. So you can go to Analyze, Descriptive Statistics, and Frequencies. But there is this is the quick version. So let's have a look at age as well. So we'll ask for descriptive statistics. Again, we can see we've got no missing data. That's very good. We can see the mean and the median. These are fairly similar, aren't they, in the standard deviation. So there's a fairly large, an 8.6 year standard deviation around the mean age. got the minimum and maximum, so we've got a fairly large range of scores, but we probably want to know more than that. But at this stage, we won't run the histograms, but we're just looking at whether we have all the data we need. So do we have any missing data that we'll need to account for? So we'll just do that for extrinsic career success as well. Okay, so we can see the minimum value is 44 and the maximum is 118. So we could contrast that with the possible range, 30 to 130, so that looks reasonable. Okay, and we can see again we've got no missing data, so everyone completed that measure. We look at satisfaction with life. Again, descriptive statistics. Okay, so we can see we have a minimum of 77 and a maximum of 209. So actually this is looking like the lower end of the life satisfaction score potentially for our sample. Obviously what you ideally would like to look at is some norming data to see, well, different populations. And at the moment we don't have any information about kind of who our sample is, just that they are employees and they're at a single organisation. Okay, so we can see that we have no missing data, and what this tells us is that we have data for 100 individuals. Okay. So one of the things you'd also need to do is consider sample size at this point. So Julie Pallant, Andy Field have guidance on sample size for regression, so you would need to look at those guides and make a decision as to how many predictors could a regression analysis with this sample size effectively run with. Okay, and as a very rough rule of thumb, we say that you need at least 15 participants per predictor. So you'd need to decide whether running a regression with age, gender, and extrinsic career success, is that feasible? So in this case it is. But that's on the very minimum kind of side of sample size requirements. So something else we might want to do is have a look at the distribution of our outcome variable. So there are some debates in the literature about whether or not the outcome variable needs to be normally distributed, or kind of the extent to which regression can handle violations of normality. So we'll have a look. When you start to get larger sample sizes, it potentially becomes less of an issue, but we'll have a look at it. So we'll ask for, we've gone into the explore function, we'll look at statistics. Those are all fine as the defaults. Look at plots. And I'm going to ask for histograms to be produced and normality plots. We'll click continue. And then options. This is where we tell SPSS how to handle any missing data we have. Now, we don't have any missing data, so we don't have to worry. We can just leave it at the default. So we'll click continue. And then we'll click OK. What we can see here is, okay, we've got something, the test of normality. And because we've got a sample larger than 50, we can look at the KS test, the Kolmogorov-Smirnov. We can see that we have a p-value there that's greater than 0.05. So that suggests that this data set is not significantly different from normal. So it looks like, for our outcome variable, it looks like roughly normal. There's something a little bit strange going on, but that looks okay. We'd also want to have a look at our box and whiskers plot here. And the box plot is really going to help us identify whether we have any univariate outliers on our dependent variable. So we can see here there are no extreme values. So an extreme value would either appear as a circle, which is a sort of moderate outlier, or an asterisk, which is an extreme outlier and you need to do something about it. So we can see actually our dependent variable seems to be performing or behaving relatively well. So that's a good sign. So what we're going to do now is we're actually going to look at running the multiple linear regression and the additional assumption checks we need to do as a result. So we go to Analyze, we go to Regression. You can see there are lots of different types of regression we could choose, but we're going to look at linear, and that's where we fit straight lines to things. So it's part of the general linear model. So we've got our outcome variable, our dependent variable, so we want to put that into the dependent box. And then our predictors, we want to put those all in at the same time, and that's because we don't have any really really fixed theory or that we're testing here. It's quite exploratory. So we're going to put all of our predictors in at the same time, which is called the default method, which SPSS refers to as enter, and it's the standard linear multiple linear regression. If I wanted to do hierarchical, I could just use these boxes to enter my predictors at different stages and to compare the stages with each other to see, adding new information about predictors in, does that help me understand my outcome measure better, or is it kind of redundant? So that's the facility you would use, this blocking here. That's what you would use to run a hierarchical linear regression. To run a stepwise linear regression, which is something that you could potentially do if it's exploratory research, although you have to be wary of the sample size requirements, so typically around at least 40 participants per predictor for stepwise, I would need to go into this, the method. So currently it's on the enter method, the standard, and I would need to choose one of these. So the most commonly used are the backward and forward methods of stepwise. And if you want to know more about that, there's some information in Andy Field's book, Discovering Statistics Using SPSS, which is quite useful. But as I said, we're going to use it as the standard method. If there's any doubt, the standard method is probably the safest one to use. Now I need to tell SPSS what information I want. So I'm going to go to statistics. I'm going to ask for the descriptive statistics again, just so it's all part of the same output. I'm going to ask for confidence intervals. Now that's an additional thing. It's not necessarily something that's asked for in the walkthrough. So as long as you are looking at, you've got a measure of error, which it could be the standard error, which you'll see in the output in a moment. You don't have to have confidence intervals, but I'm going to bring them up to decide whether I want to report standard error or confidence intervals. Standard error and confidence intervals are kind of calculated from the same information, and they give you an idea of how accurate your estimate is in the regression. So the greater the error, the less accurate the estimate. So, and there's always a degree of error. So we'll want to see how much error. So we'll get a sense of that from this. Next, I'm going to ask for part and partial correlations, and what I can use this to do is actually to understand the unique relationship between a predictor and outcome. So whereas the model fit will give me an idea of how the predictors in combination explain my outcome variable, or the variance in my outcome variable. The part and partial correlations can help me understand the unique ability of each predictor to predict the outcome, so how it contributes uniquely to the model. So I'm going to ask for that. Now it's important to remember that if you have chosen, you've got missing data and you choose the pairwise deletion method, this becomes a lot trickier to interpret. But as we don't have any missing data, we don't have to worry about that in this sense. And I'm also going to ask for collinearity diagnostics. That will help me to test the assumption of collinearity. I'm going to ask for the Durbin-Watson because I know the order in which my participants completed the study. All of this information is in the walkthrough, so if you have any concerns, don't think you have to remember these steps. You just need to know where to look. And so there are some really good guides at the walkthroughs, and I would recommend Julie Pallen's SPSS Survival Manual as well. It goes through step by step on how to conduct regression analysis, ANOVA, MANOVA, and factor analysis, so it's a really good book. Next, I'm going to click on the plots option. Now this is where I can test some more of the assumptions. So if I've got my model is good, it will be equally good at predicting people's scores at the low end of the satisfaction with life scale and also at the high end. So what I'd expect to see is the error in the model will be normally distributed. So that's one of the assumptions, normality. So I can use these plots to help me decide whether my data meets that assumption or not. So I'm going to choose, this is the standardized predicted value and the standardized residual value. I'm going to enter those. I want that to be produced. Now, you can choose produce all partial plots, and what this does is it creates a scatter plot of your predictors with your outcome variable, so you get an idea of the strength of the relationship, the direction of the relationship between predictors and outcomes. So that's quite useful. But you can also ask for a histogram and a normality plot for the standardized residuals. So this isn't something that's in your walkthrough, but this is an additional check you could do. Traditionally, the assumption of homoscedasticity, if I can say it, normality and linearity are assessed using this method, but actually normality, it can be easier to look at it from here as well. So then I'll click continue. Next I need to go into save. And there's a whole host of things I could ask it to produce here, but what I really want is these measures, these distance measures. Now, I want the Mahal distance, and this will tell me whether I have any multivariate outliers in my data set. So multivariate outliers are those which are represent an unusual combination of scores across variables. So if you looked at them individually, they wouldn't necessarily look out of place, they wouldn't look like extreme values, but when you bring them together, they look like an extreme case. Now, even if you do have multivariate outliers, sometimes they can only be marginal and not actually affecting the performance of the overall model, so it can be safe for you to leave those multivariate outliers in there. In other instances, the multivariate outliers will have an extreme impact on your model's ability to predict your outcome variable, and you need to really think what you're going to do with those cases. And a measure of that is the Cook's distance. So I'm going to ask for those two things. And we'll look at interpreting those in a little bit. So if I click continue, next thing I can look at is the options. Now this is where I would tell SPSS how to handle missing values. And I would recommend having a look at Andy Field's book about the impact of handling missing values in regression. We don't have to worry about it in this example because there isn't any missing data. But this is the point at which really we're going to need to decide between either listwise deletion or pairwise. But we don't have to worry about that in this instance, so I'll just click continue. So now we've told SPSS what we want, so we'll get it to perform the regression by clicking OK. Okay, so this information tallies with what we were expecting. So we've got the mean statistics, obviously for gender, that doesn't make so much sense. We can see that our sample size is 100, we can get an idea of the spread of the data around the mean. The next thing we're looking at are the correlations. Now, to interpret this, what are we looking for? Well, we want to know that our predictors are related to some extent with our outcome variable. So our outcome variable here is life satisfaction. So we want ideally these to be moderately correlated to strongly correlated with our outcome variable. So we can actually see that gender has a kind of moderate positive correlation, and age has got a negative correlation, and extrinsic career success has a negative correlation. So that's quite interesting. What we're also looking at is, do any of our predictors have a very strong correlation? Now, if the predictors are too highly correlated, what you can potentially end up with is multicollinearity, and regression won't work well. So you'd have to look at either combining your predictors in some way or dropping them and looking at them separately in separate regressions. But really we'd be looking there if we've got correlation coefficients of 0.8, 0.9, then we've got a problem. It doesn't look like there are any issues here. This box simply tells me what my dependent variable is, and that I've performed the enter method, which means that all of my predictors have been entered at the same time. So we can see what our predictors are, and we can see what our dependent variable is. And if you've got large numbers of variables, it's good to check this to make sure that you have used them in the way that you'd intended. That all looks okay, so we can go on. The next piece of information we have is the model summary. So this is where we have the R, which is the correlation coefficient, R square, which is where it tells us basically the model fit, and adjusted R squared. So it's recommended that if you just want to talk about your sample, you can use R squared, but if you want to try and make generalizations to the population that your sample was drawn from, then you should really be using the adjusted R square. And what you can do with these R squared values is multiply them by 100, and that gives you an idea of the amount of variance that your predictor variables in combination can account for in your outcome, which is satisfaction with life in this case. So we can see that knowing extrinsic career success, knowing someone's age and gender, has been able to account for 42% of the error, 42% of the variance in life satisfaction scores. Now that's quite a hefty amount, especially in the social sciences, so that's definitely worthwhile. What we can't tell from here is whether that is statistically significant, or if we could have achieved the same degree by essentially guessing. So we'll need to look at some other information to decide whether our model is statistically significant. Now I mentioned the Durbin-Watson, and this is in your walkthrough as well. But the Durbin-Watson, the closer that value is to 2, the better. So what we can see there is that value is it's not perfect, but it's pretty close to 2. What that suggests is that the scores of one person, the kind of the error in the model for one person, is not impacting on the error in the model for the next person's observations. So that suggests that we've met the assumption of independence, and that it hasn't mattered the order in which participants have completed the study. So that's a good sign. The next box is the ANOVA table, and this is where we can tell whether our model is statistically significant, or whether essentially we could achieve the same kind of results, the same kind of accuracy, by guessing using the mean scores only. What we can see here is that we have a statistically significant result, so that is less than 0.05. So in combination, our predictors are highly statistically significant, and we know that they significantly account for 42% of the variance in life satisfaction. So this warrants looking at that model in further detail. So we want to see, is this model being kind of informed equally by knowing extrinsic career success, age and gender, or perhaps there's one that's particularly strong at predicting satisfaction with life and the other's kind of a bit redundant. So we need to know more, and the information we need to look at is here. So in here we have the coefficients table, and this coefficients tells us a whole range of things. So the first thing is that we want to look at are our collinearity statistics. Now these statistics give us an idea whether our predictors are too highly correlated, that they share too much variance, that essentially you're kind of almost measuring the same thing twice. And you need to look at stripping back the model, removing one or more of the variables. So what we're looking for here is a VIF value greater than 10, or a tolerance value of less than 0.1. So that would be a problem. As we can see here, those are both looking good. So there's no particular problem, and in relation to the correlation coefficients we looked at earlier, that kind of supports that evidence. So there doesn't appear to be a problem with multicollinearity, so we can retain all of our predictors based on that. There's one more assumption check that we probably want to do before we get carried away looking at these standardized coefficients, and that is contained in the residual statistics. So residuals is a fancy word for error. What we're really interested in are the Mahal distance and the Cook's distance. Now this represents a value, Mahal distance, the furthest distance for an outlier. Now you can look at tables of critical values that tell you whether that value is larger than the critical value, and therefore you have at least one multivariate outlier. So if that was the case, you could look back at your data set. What we've got here is actually a new column. So this is the Mahal distance for every single variable and its associated Cook's distance. What we can see here is that's probably the culprit. That's the largest multivariate, the distance from the centroid. So it's the biggest Mahal distance. So if anything's going to be an outlier, it might be this case here. Now I'm going to focus on something called the Cook's distance, because even if there are technically multivariate outliers in our data set, they're not necessarily exerting an undue influence on the model. And And the way that we can tell that is to look at this Cook's distance value, and we're interested in the maximum value. Now, if the maximum value reported here is 1 or greater than 1, you have a multivariate outlier that is having an impact on your model, and you need to look for it. It could be more than 1. So what you'd need to do is you'd need to look through your data set and find them. So you'd see a value in here of 1 or greater, and the larger the value, the greater the impact that that case is having. Now we can see here, obviously, that none of those values are 1 or greater, and so actually, even if there are technically any multivariate outliers, they're not having a huge impact, so we don't have to worry about it. We can retain them. We'll also have a look now at the normality assumption. We can see here that actually the predicting scores either the low end or the high end of our outcome variable. The model's roughly, the error is normally distributed. So actually it's fairly good. There's nothing, it's not better at predicting scores that are higher up on the scale or lower. And what we're looking for really, ideally we want this in, this is the standardized residual plot. What we want is everything in a nice kind of rectangle. So there's a spread of the scores across the values, and there doesn't seem to be any particular pattern. What we'd be particularly concerned with was if there was a very clear funneling effect, so very narrow range of dots clustered here, for example, and then spreading out to a huge range. What that would suggest is that it's better at predicting scores at the higher end of the outcome variable than it is at the lower end, and what you've got there is there's something systematic going on with the data, and that might mean that it's not actually a linear relationship between your predictors and your outcome. You might actually need to do something to the data before we can use a linear regression. This isn't perfect, but actually in combination with looking at the normality, looking at this plot here, which helps you identify linearity and homoscedasticity, these things look okay. There's nothing too concerning in this. As I said, all of this information is in your walkthrough, so you can check it. But there's quite often with statistics, it's no definitive answer. You just need to look at this and try and make a decision based on your judgment and knowing the context of the research. So our assumption checking suggests that things look okay, that the data looks like it's performing in a way that means we can run a linear regression. We have found that the model is pretty good at predicting variance in our outcome variable, that it's statistically significant than chance at predicting the outcome variable. And what we want to know now is, okay, well, these are our predictors. Which is the strongest predictor? Now, the best way to do that is to look at your standardized betas. Standardized betas, these are actually standard deviations. They've been standardized, so it doesn't matter what unit of measurement they were originally measured in, we can now directly compare between them. A positive number means that there's a positive relationship between the predictor and the outcome. A negative relationship, a negative means a negative relationship between the predictor and outcome. So what we can see here is, regardless of the size, the strongest predictor is the extrinsic career success and that's similar to gender. And when we're looking at the significance values, we can see that all of those predictors are actually statistically significant, but the strongest is probably this extrinsic career success. So the standardized coefficients can help you decide, well, which is the strongest predictor, so that if you're wanting to perhaps use this to help inform a practical intervention to increase satisfaction with life, you could pull out which are the variables that I really need to focus on, that I need to kind of explore. And obviously you can't manipulate someone's gender in any way, but perhaps you could look at why extrinsic career success has the strongest relationship, followed closely by gender, and trying to unpick that relationship further in terms of satisfaction with life. In terms of actually putting that into real terms, when we're looking at things like age, the unstandardized coefficients can help us look at are the relationship between the predictor and the outcome in the original units of measurement. So for every 1 unit change in age, so for every year older you become, your satisfaction with life will go down by a point on that scale, by 1.01 points on the satisfaction with life scale. I hasten to point out this is a fictional study, so don't please get too despondent. Extrinsic career success, what we can say is that for every point on the extrinsic career success scale you go up, your satisfaction with life score will actually decrease by 1.2 of a score, of a point on satisfaction with life. So, and that's actually contrary to perhaps what we were anticipating in the original, at the beginning, before we ran this analysis. We might have predicted that extrinsic career success would be associated with greater satisfaction with life. Well, this research is suggesting the opposite. But it's doing that when you've accounted for gender and age. So one of the benefits of using a multiple linear regression is that these coefficients tell us about the unique relationship between career success and satisfaction with life, holding age and gender constant. So we can look at untangling the effect, and looking at kind of the unique relationship between these factors and the outcome variable. So gender is slightly more difficult to interpret. We can't say that for every unit of gender you increase, your score will go up by 34 points. But so we need a different way of interpreting that. And to be able to do that, we need to look back at the data. And specifically, we need to look at how males and females were entered, how they were coded. And this is something called the value labels box. So if I want to look at the raw numbers underpinning those categories, if I turn that off, that's what I see. So we can see that there's a 1 there, a 0 there. So males were coded as 1 and females were coded as 0. Now when you have categories, categorical data, in regression, it's really important you know exactly how you coded that data. So if we look back at the outcome variable here, so the output, to interpret this, what we need to know is who was coded as 1. So males were coded as 1. So that makes our reference categories females. So in relation to females, males scored 34.5 points higher on satisfaction with life. So males scored 34.5 points higher on satisfaction in life than females. So it's whatever is coded as 1. If it's a positive number, they scored that much more than your reference category, which is coded as 0. If it was a negative number, then whatever was coded as 1, so males in this case, would have scored that much lower than the reference category, which is females in this case, as 0. So it can tell you quite a lot, these kind of regression coefficients. Another really useful tool when you don't have any missing data or when you've applied listwise deletion are these correlations. So the 0 order correlation is essentially just a Pearson's correlation. So correlation between gender and satisfaction with life, and we can see that correlation here. What's very useful is when we look at the part correlation. So the part correlation, we could square that number and then multiply it by 100, and that will tell us the unique percentage of variance accounted for in satisfaction with life by that predictor. If you'd done pairwise deletion with missing data, it becomes much harder to interpret those, and in fact I would steer away from it if you've done pairwise deletion. Okay. So what we can see then is that we have a model that's really useful. It's predicting 42% of the variance. That's pretty good considering the context. But actually the relationship between one of the variables is in the opposite direction to what we kind of anticipated. But actually that gender is also another important variable. And so what we might want to be doing is thinking about, well, how can we use this information further? What is it then about extrinsic career success, which the greater amount that you report, you self-report, having is associated with greater satisfaction with life. is associated with less satisfaction with life. And we need to unpick that further. So you perhaps look at that in terms of further research, and then using that information to perhaps build some kind of training, some kind of intervention that could help focus on the role of extrinsic career success in satisfaction with life. So as you've gone through that, have a go at answering these questions and thinking about them as we've sort of discussed in that video, and have a go at kind of drafting some answers yourself. If you have any questions, please let me know, and I'll be happy to answer them. Okay, thank you.